Welcome and good day from group 4. So today we are going to present about experiment 4, which is vapor compression refrigeration. Our group consists of me, myself, Afan, RC, and Haikal. So I will present the abstract. So this experiment is about the process that happens in refrigerator. So this experiment, we are required to determine the coefficient of performance, or COP, for vapor compression cooling system. To accomplish the objective of this experiment, QH and the value of QI will be determined. We should plot the graph, and from the graph that we have plot, we can put that the flow rate is inversely proportional to the temperature. Condenser flow rates also shows that it is inversely proportional with the power, or W net. As I said just now, the objective of this experiment to determine the coefficient of performance, or COP, for vapor compression of cooling system. For the introduction, refrigerator is a cyclic device for heat from low temperature to the high temperature. The fluid, which called refrigerant, or R/141B, which was used in this experiment. Refrigerant can undergo phase change from liquid to superheated. It can turn back to liquid as it is passes steadily through the various components that comprise the system. So the system have 4 components: a condenser, thermal expansion, and evaporator. I will pass to next presenter.
Hello and good evening. My name is Muhammad Daniel Haikal bin Hasbullah, A19ET0124. We'll be explaining about two things, which is the theory and methodology, which is procedure. So theoretically, a cooling system actually accepts the heat from the lower temperature space and heat transfers to the high temperature space. It actually requires work, W, which is to be supplied to the system as shown in figure 2. So Q1 is just QH, which is the magnitude of heat rejected to the warm space. Q2 is QL, which is magnitude of the heat removed from the refrigerated space. So next slide. So what is the working principle of a refrigeration system? Well, when the refrigerant, working fluid, which was already explained by Afan earlier, come to the compressor as a vapor and compress due to the condenser pressure as shown from the figure 2, it actually exits the compressor with a high temperature. Then it cools down and condenses as it moves through the condenser coils, actually freeing heat to the environment. After that, it actually reaches the capillary channel, where the throttling effect will cause the pressure and temperature to actually drop. The low temperature refrigerant is then pumped into an evaporator, where it absorbs heat from the refrigerated space and evaporates again. The cycle is considered complete when the refrigerant leaves the evaporator and re-enters the compressor. So below is the equation of coefficient of performance, which is COP. COP is equals to cooling effect divided by work. This is going to be explained further by someone in the results sections.
Okay, my name is Muhammad Arsi, and I will continue with the presentation on apparatus, result, and calculation. For the apparatus, consists of temperature selection switch, condenser, valve, main switch, temperature indicator, evaporator, and compressor.
So I'll be explaining about methodology or procedure now. So from the first step is actually from the picture we can actually see the two arrows. Those two arrows are actually pointing to the valves. So these two valves actually needs to be open before we start the experiment. The second step is actually to turn on the water pipe and set the water flow of evaporator and condenser to 26 grams per second, which is on the right is the evaporator, on the left is actually the condenser. So next slide. So the third step will be switching the cooling system on. After that, it will be left for a while, for an approximate of at least 10 minutes, at least 10 minutes for it to be stable. So next slide. So fourth step would be the temperature, recording the temperature of T1 until T4, which was obtained by actually adjusting the temperature selector switch, which is below the temperature indicator, and the temperature was recorded as shown from the temperature indicator. The fifth step would be taking the pressure of the condenser and evaporator from their own gauge, which is the left is the pressure gauge for the condenser, and the right is actually the pressure gauge for the evaporator. So next slide. The sixth step is actually the temperature of T5 until T7 was recorded manually. So T6, which is the condenser, there's a slight calculation here. T7 is actually the evaporator, and T5 is the compressor. So the seventh step is actually the experiment was repeated by changing the flow rate of water for both evaporator and condenser, which is between 26 to 4 grams per second, and then it would be repeated 4 sets for each of the changed flow rate of water. So that's all for my part. Thank you.
Okay, this is the result of the experiment. Okay, for the calculation of rate of heat transfer at evaporator, M equals to 0.018 kilogram per second. We use a formula Q equal to M delta H. For Q1 is equal to H at 31.5 degrees Celsius and H at 29.8 degrees Celsius. For this H value, we need to do interpolation because no accurate data from steam table or something like that. So for Q1 is the value is 43.80 kilowatt. For Q2, do the same thing and equal to 43.77 kilowatt. Q3 43.74 kilowatt. Q4 equal to 43.69 kilowatt, and Q5 equal to 43.66 kilowatt. And for the rate of heat transfer in condenser, Q1 for condenser we use different M, which is for test every test different M. For example, Q1 the M is test 1, the M is 0.018 kilogram per second. For test 2 is 0.016 kilogram per second. Okay, for the rate of heat transfer in condenser, Q1 equal to M, H 30.6 degrees Celsius and H 29 degrees Celsius. Okay, for H, we use the gas state minus the liquid state. Okay. For Q1 equal to negative 43.65 kilowatt, Q2 equal to negative 38.66 kilowatt, and Q3 negative 28.94 kilowatt, Q4 negative 19.26 kilowatt, and Q5 equal to negative 9.59 kilowatt. Okay, I will continue with calculation of coefficient of performance COP. For this calculation, we use a formula COP equal to modulus QL divided by QH minus QL, which we got COPR equal to 0.5. COPR2 equal to 0.53, and COPR3 equal to 0.6, COPR4 equal to 0.96, and COPR5 equal to 0.81. Okay, this is the graph that we obtained from the value that we got from the calculation. Okay, I will pass to Afis to continue the presentation.
Hello everyone, I am Muhammad Al Hafiz. I'll present about the discussion and conclusion part. So for the discussion, the first question is explain the effects of changing the condenser flow rate of T1 until T5 to compressor power and discuss the result. The graph 1 which is made by RC, as the flow rate increase, the temperature of all tests is decreased except for the test for test 5. As a result, the rate of heat transfer in the condenser is inversely proportional to the rate of water flow. The temperature of water passing through the evaporator and condenser, which is between T1 until T4, will be affected by the changes in condenser flow rate. Since the refrigerant are 1 for 1B that enters and leaves the evaporator is saturated, the temperature of T1 and T2 are almost unaffected by the changes in condenser flow rate. T3 and T4 values decrease as the condenser flow rate increase, whereas for the value of T5 it is increasing when the flow rate of condenser rise. As for T6 and T7, the value decrease as the flow rate increase. As you can see, this is the graph for graph 1 and graph 2. Based on graph 2, the graph shows the compressor power input against the condenser flow rates T1 until T7. It shows that the compressor power decreased during test 1 and dropped drastically during test 2. During the experiment, error that might occur in this experiment is the value of compression power, in which these values keep changing with time. Thus, the values were not accurate. The accuracy of the data taken, take the average. To increase the accuracy of the data taken, take the average values of the temperature of T1, T2, T3, and T4. The joint at the pipe may be loosened, causing leaking at the joint, and this will make the flow becomes unsteady. The machine maybe is not in a good condition. To overcome this problem, make sure the joints are connected tightly to avoid leakage before starting the experiment. In addition, make sure there is no air bubbles that present inside the pipe because it will affect the result obtained. To avoid this error, let the water to eliminate the bubbles that may be formed in the pipe before starting the experiment. So, as a conclusion, the coefficient of performance, which is COPR, is directly proportional to the rate of heat transfer of evaporator QN. It follows that the condenser flow rate is proportional to the compression force. On the other terms, as the condenser flow rate increase, so does the work input. Last but not least, it can be said that the flow rate of the condenser is inversely proportional to the rate of heat transfer. From our group, thank you.